Hello everyone. Uh, let's continue the discussions on columns. We are in the we are going to discuss the design of columns for biaxial bending in this module. So this is in the fourth part of the module that we are discussing on design of columns. In this chapter, we are going to discuss about behavior and design of short columns under axial compression with biaxial bending. Okay. So what are the expected learning outcomes? The student, after watching this video, he or she should be able to differentiate the behavior of columns that are subjected to uniaxial and biaxial bending along with compression. What are the difference between uniaxial and biaxial bending? And should be able to explain how the interaction diagram or surface looks, the PMX-MY interaction diagram for columns that are subjected to biaxial bending. In fact, this is a three-dimensional surface that how to derive that we will talk about that. And then we will go through the code provision that exists in IS 456 on how to account for this biaxial bending and what are the procedure that is laid out in IS 456. And then we will also look at one example of designing a column that is subjected to biaxial bending. Right. So we know that columns in the last three parts of the module, we were discussing about what is a column, what is the difference between short column and slender column. And then in the third part of the module, that is the last week module, we discussed about how to derive the axial compression bending interaction curve. That is actually uniaxial bending. Right. So columns, as we have discussed in the first part of the module, if the load is applied in the geometric centroid without any eccentricity, they will be subjected to pure axial compression. But most often, we will have eccentricities. In fact, the more generic loading is, columns will be subjected to axial compression and it will be eccentric with respect to both major and minor bending axes. So in this case, what we are looking at it is, for example, let's say this is the column that we are looking at. My load is actually at eccentricity with respect to, let's say this is y-axis, and here we write that eccentricity as Ex. Okay, so though here basically the major axis of bending here is the y-axis, right? And you have eccentricity which is measured perpendicular to that bending axis, which we, when we measure the eccentricity along that axis, we call that eccentricity. That's why we are writing that as Ex. Okay, so this kind of uniaxial bending and axial compression is very common. However, for example, for columns that are located in the corner of the building, even under gravity loads, you will have bending about both axes because you see that the tributary area will have basically you will have a truncated corner area where that whatever the load that is subjected in that area will be transferred as biaxial bending. So this is a more generic case where you can see that the location of this P is at an eccentricity Ex, okay, and also it is at an eccentricity Ey. So this, if you look at, if you convert this into an equivalent system of forces at the center, how the forces are going to look like, you will have basically Pu. In addition to that, you are also going to have a bending moment My, which is, let's say this is your axis Ey and this is X. So if I'm taking bending moment about Y axis as, then I have to multiply this Mu, which is basically, let's say Muy in this case, Pu times Ex. Actually, this should be Ey. Okay, this should be Ey and this should be Ex. Okay, similarly, you will also have other bending moment which will be subjected to, let's say this is Mux that will be equal to Pu multiplied by Ey. Because if I take bending about this axis, this force it's at an eccentricity Ey. So that is why we are writing the bending about x-axis as Pu times Ey. Okay, this is the sign convention that we are going to form. So for example, for this column, you have axial compression at an eccentricity E1 and Ex with respect to x and y axes. That is going to create biaxial bending. Right? Uh, if your eccentricity about one of the axes is very small, then we can say that the column is predominantly subjected to uniaxial bending. But you know that code always mandates you to consider some minimum eccentricities that we discussed why we should consider the minimum eccentricity in calculations of the moment in the last part of the module. Your column may not be straight, your live load patterns you may not be sure, right? So there is various reasons that we discussed in the last part of the module why we need to account for minimum eccentricities in design. Now, you can see that biaxial eccentricities are significant in the corner columns of the building. So that we discussed, right? So because the tributary area is basically one corner area, whatever the load that is applied, that will basically transfer into bending moment about both axes. Right. So all the columns we have discussed that should be designed for minimum eccentricity about both major and minor principal axes of the section. So in this case, if you look at it for a rectangular column, in this case, this is your major bending axis and this is your minor bending axis. The reason is because the the dimensions which is perpendicular to the x-axis is small. That is why here the x-axis we are calling that as minor axis and y-axis we are calling that as a major bending axis. So depending upon your dimensions, these principal axes, major and minor principal axes will change. Now, if your eccentricity about one axis, if it is going to be very small, for example, in this case, let's say Ex is very small, let's say about 5 mm or so. Okay, then we can say that this column will be subjected to predominantly axial compression and uniaxial bending. Okay, uniaxial bending. Okay. About only one axis. That's why we call that as uniaxial bending. Right. So in this case, let's say Ex is 5 mm and Ey is let's say 30 mm. Okay. So we know that now the Dx is only 5 mm and that's not really going to create a major bending about y-axis. So you will have moments only mx, pu and some nominal moment mey that we need to account for in our design. Okay, so this is what we are saying. If let's say if eccentricity is, sorry, this is correct. If this eccentricity is small in both the axes, in both the cases, let's say ex and ey is only 5 mm, then the column can be considered as predominant to subjected to only axial compression with very less bending. So the bending effect is not going to be very significant. But you can also have a case that EY can be higher and EX can be very small, or one of the eccentricities can be very small compared to the dimensions or the axis or the dimensions. Then we can say that the column is subjected to axial compression and uniaxial bending. So you have all the combinations that are possible. So in summary, if your eccentricity is very small about both the axes, then the column will be subjected to predominantly uniaxial compression. And then if the eccentricity is very small only about one axis, then you will have axial compression and uniaxial bending, but not biaxial bending. But Ex and Ey are significantly higher, then you need to account for this biaxial bending. Now let us see. So we talked about how to derive that axial compression, bending moment interaction for uniaxial bending, right? Now we are talking about biaxial bending. Let us look at it. Now when I want to create that, and we also saw that the axial compression bending curve is going to be, this is what we have looked at it, right? So we put Pu in the x-axis, sorry, y-axis, and Mu in the x-axis. Then for a particular cross section, we know how to calculate and then get this curve. Okay, so you know your dimensions of your cross section and you know what is the area of steel that you are going to have. So once all the dimensions are fixed for this particular, let's say you are given FCK and Fy of the grade of steel, then I can derive this. This is we call that as also failure curve. Okay, so and right, so this is the failure curve. So this is a capacity curve or failure curve. This is the maximum capacity that particular cross section can take. Now this we did by how did we get this? What we did, we we fixed the top compressive fiber strain and varied the neutral axis. Or in other words, for depending upon the neutral axis that you're assuming, again epsilon cu is also going to change. That also we discussed, right? So once epsilon cu and neutral axis depth is fixed, then your strain profile is fixed. For a particular strain profile is fixed, then I can use axial equilibrium and moment equilibrium about both the axes to find combinations of PU and MU that will create failure. So then we get different points, right? We do the example, we did pure compression, pure bending, and then different combinations that we get. So for uniaxial bending and compression, what we get is a failure curve. It is a curve, okay? But here we are talking about biaxial bending. So if you look at the capacity, then it is not only going to have, let's say, a bending moment capacity about one axis, you are going to have bending moment capacity about other axes. So this uniaxial bending and axial compression curve will be a special case of biaxial bending. So let us look at now how different cases can come. So let me erase this. Right. So let's look at it. For the first case, okay, in this case, for a rectangular section that we have considered, and this is your major axis of bending, which is your y-axis, and that is why I am writing perpendicular to the y-axis eccentricity as Ex. Now you see here the Pn, which is actually moving along the x-axis. Okay, so it is not uh, if you look at the eccentricity Ey in this case eccentricity Ey is actually 0. Basically the Pn, if I keep moving from y-axis along the x-axis, you will have only Ex. Ey will always be 0. So then we call this kind of cases axial. It has an axial compression of P and it is also moving along the x-axis, means you are going to have bending moment. Now what is bending moment? Bending moment is about my will be P multiplied by Ex. Depending upon the value of Ex, now bending moment is going to increase, right? So this is a case of a uniaxial bending. You have only P and My. Okay, so that's why we are writing this. So we can get this capacity curve like this. Okay, so we can get this capacity curve like this, like what we have discussed in the last class, right? So this is the case. Which has only special case of a biaxial bending case. And how do you find this? Again, the neutral axis also, if you look at it, we have looked at different cases. Neutral axis can be within the section. Neutral axis can also go outside the section. Depending upon the value of neutral axis, we also fix the value of your top compressive fiber strain, right? Which is basically uh, 0.0035 minus 0.75 times epsilon c minimum. Epsilon c minimum is the compressive strain at the least compressed stage. So we derived that using similar triangle, right? So, but what you can note here is this is basically your depth of your neutral axis, okay, or XU. So let me write that as XU, okay. So for uniaxial bending, you find that the neutral axis, which is this axis, is always parallel to the axis of bending. Okay, so the neutral axis is always parallel to the axis of bending. In this case, the axis of bending is y. So your neutral axis is going to be parallel to the axis of bending. Now let's look at the another case. Now I am having axial compression force which is located at an eccentricity with respect to x-axis. However, it is moving the P, let's say if it is moving along the y-axis, I am going to generate only uniaxial bending about x-axis, right? So then this becomes your special case. Okay, so we get this, right? So this is, you have only in this plane, you have P and Mx only, right? So that's how we get this case B. Here also you find here that your neutral axis depth is actually, this is your neutral axis. It is actually parallel to the axis of bending. Now, what is the axis of bending? Which is x. So, the neutral axis will be always parallel to the axis of bending. So, we have seen the first case here also. The neutral axis parallel to the y-axis. In this case, the second case, what we are talking about, neutral axis parallel to the x-axis. So, this is the way we get. So, once your dimensions and reinforcement details are given, then we should be able to get this capacity curve, which is PMY as well as PMX. Here it is written as a capacity, right? So these two special cases we can get. We can also have another special case where axial compression is zero and you have bending moment only about both axes. That is also possible. So that is this. Okay, so this is this case. So what is this case? Here your PU is 0. It is a special case where no axial compression. The section is subjected to only biaxial bending. That is bending moment about y and x axis. Right. So this is a special case. Now this is a more generic case would be when your axial compression is at an eccentricity with respect to both x and y axis. Okay. So in this case, if you look at it, you have this is your axial compression location. Now you see that this is having eccentricity of EY with respect to x axis, and you have an eccentricity of EX with respect to y axis. So what would be the bending moment My? P multiplied by x. What would be the bending moment about x? Mx will be P multiplied by eccentricity E1. So this column will be subjected to axial compression P, bending moment Mx, and bending moment My. So you have all the three combinations. In this case, if you look at it, your neutral axis will not be parallel to the axis of bending. So your axis of bending is going to be this green color that what we have seen. Okay, so if you see here, this is your axis of bending. Okay, however, your neutral axis is actually will be at an angle. We don't know what that angle to start with. So this will be at, let's say, with respect to x-axis, that I'm going to have this neutral axis is going to make an angle theta, but you see that now the neutral axis is not parallel to the axis of bending. So how do I get this axis of bending lambda? We can get, because basically if I am this angle, let's say this is with respect to x and y axis, your P is moving along this direction. So this, if you know this Ex and Ey, that slope will be that if you draw the line, that whatever that line that makes perpendicular to this the load where the ratio of Ey by Ex, then that would be your um, axis of your bending. Okay, so if you see here, so in this case, then you will have uh, if you take any point on this curve where you will have capacity axial compression, then you will have mu capacity of bending about the x-axis, and then capacity of bending about y-axis. So you will have all the three values that you will have, right? So so if I move along this, so basically for this one particular case, this is, we can call this as a plane of constant lambda, and lambda is, now it is going to be at an axis with respect to your y-axis, because now if you see here, Mnx is bending moment about x-axis, where eccentricity is going to be Ex. So that is the reason the angle here, lambda, is going to be uh, making an angle like this. So with respect to this, this would be this, your lambda. Okay, this is a very special case. What you have to note here is, here the neutral axis is not going to be parallel to the axis of bending, where your axis of bending is this, which is making a 90-degree to this, where the P is moving at with the constant ratio of, let's say, U by X. Then that angle, the line that is perpendicular to this load moving axis is basically your bending axis. Okay, so yeah, so this is a special case. Now you can also have another plane of constant axial compression. Okay, so the plane of axial compression. So in this case, any point what I'm taking, either here or here or here or here, my this third axis, P axis, is kept. That means the value of axial compression is going to be constant. Okay, for particular value of axial compression, so you can have this particular shape of the curve. That again, this shape of this curve, right? So that is going to also change depending upon what is the level of axial compression that you have. Okay, so for example, if you look at it, if I'm taking here, so this is what we call that as a load contour, and if wherever this is hitting this uniaxial case, this is your uniaxial bending capacity. Okay, about in this case it is about y-axis. Similarly, this point, okay, which is this is basically uniaxial bending capacity about x-axis. Okay, now these all these things is at the value of p, one particular p. This is also at one particular value of p. If I'm changing this p, again the uniaxial bending moment capacity is also going to increase. That's what we have seen in a particular curve. Okay, if I change my p, for example, let's say if I take at this point, okay, right, so this would be your uniaxial bending moment capacity about x and y for this p. Okay, but now the p value is increased. Similarly, if I'm taking at this point, you see here, what would be at p is equal to 0, this is your uniaxial bending moment capacity about both the cases. So that we can find out. It's a special case which we can find out. And what is also you have to see here is the shape of this curve between how this capacities, bending capacities are changing is going to also, the whether I'm taking here or here or here, that curve or the interaction between mx and my is also function of what is the level of axial compression that is acting on this particular uh, location, right? So we have looked at multiple cases here. What are the cases that we have said? We looked at first the very first case of uniaxial bending about y-axis, which is the case A, and then we looked at special case of uniaxial bending about x-axis, which is your case B, and then we looked at the bottommost location where axial compression is 0, where you have only interaction between two bendings. There is no axial compression. Then we looked at case C, which is a generic case, okay, where you have bending about both the axes. For that, I have to generate this curve, and we call that as basically plane of constant lambda, and we have found that the neutral axis is not parallel to that bending axis, right? So these are the things that and also we looked at, depending upon the level of axial compression, the interaction curve between two bending moments are going to change, or the shape of that interaction curve is going to change. That is why we call that as a load contour. The interaction between mx and my is going to change depending upon what level of axial compression that you're looking at. That's why we call that as a load contour. This very generic case, okay. In case of, let's look at first the circular section. So circular section, it is an axisymmetrical section. Okay. So circular sections, wherever your axial compression, even if we have, let's say, uh, this is moving at an eccentricity, let's say with respect to this, let's say this is EY and this is with respect to EX. Okay. So you will find that because the section is axisymmetric, and the resultant axis of bending, we can, of course, we can find that out. Okay, so if you know the axis along with this is moving, so perpendicular to that is your resultant axis bending, and you will find that the neutral axis will always be parallel to the resultant axis of bending because the section is axisymmetric, right? So we can somehow we can convert this biaxial bending into an uniaxial bending, and you can quickly solve for circular section. Okay, so this is a very special characteristic of a circular section because it's an axisymmetric section, and always, even if you have biaxial bending, it can be converted into equivalent uniaxial bending, and you can do the analysis. Right? In this case, irrespective of whether you have Ex or Ey, always your neutral axis will be parallel to your resultant. Now, so let us look at for the generic case. Okay, so if I look at this particular rectangular cross section, okay, so RC rectangular cross section. So what is that we have? Let's say we have axial compression, okay, which is this. In addition to that, if I use this right hand rule, then you have bending moment about, and then you have bending moment about y-axis, okay, which I am calling that as demands, which is bending moment about x-axis and y-axis. And you find that you have to your resultant bending axis for this is going to be like this. Use a different color. Your resultant bending axis is going to be like this. Okay, and if you know your, again, if you know your ex and ey, you can find this resultant axis of bending. Let's say this is your uh, ex and this is your ey. So if you know the ratio, you can calculate what is the resultant bending axis. Okay, and we have seen that for a biaxial bending case, the neutral axis need not be parallel to the bending axis. Okay, so when we did the interaction curve, what is that we did again? We varied only the neutral axis depending upon the neutral axis location. Again, epsilon cu also was changing. If your neutral axis was within the cross section, we took epsilon cu as 0.0035. Once the top compressive fiber strain and neutral axis is fixed, then using your axial force equilibrium and moment equilibrium, we were able to find that Pu and Mu, which was creating that strain profile. In this case, now I have to satisfy all the conditions. I have to satisfy axial force equilibrium, moment equilibrium about x-axis, and moment equilibrium about y-axis. Now, so the neutral axis, we have seen that it need not be parallel to this bending axis. So we should not only vary the neutral axis, we should also vary that angle. Okay, how much angle that it is going to make, so that it will satisfy that equilibrium condition. So for one particular neutral axis and one particular angle of the neutral axis, I will get, so I fix xu, and then I also fix the angle of your neutral axis. Okay, then what I get is one pu and one mx, or let me write that mrx, and then mry. So I get one point in that surface. Okay. So then what I do, I keep for the same xu, Now what I'm going to do, I'm going to change my neutral axis depth to, let's say, theta 1 and a. Okay. Then I get another value, pu 1, let's say mu rx 1 and mry 1. Like that, I, for one particular neutral axis, I can keep on increasing this theta from 0 to 180 degree. Then you get different values of this combinations of axial compression and bending moment capacities on the failure surface. So in this way, then what I do, once I do that, then I go ahead and increase my xu to, let's say, xu1. Then I go ahead and keep increasing theta 1. Now xu1, let's say xu1, and then you put theta 2. So you not only vary your neutral axis depth, you need to also vary that angle of your neutral axis depth, and you get 1 point. Okay. So once you do that, then your strain profile is fixed, and you have to integrate also. Now you see, for uniaxial case, it was pretty straightforward, right? So once your neutral axis, because neutral axis is going to be parallel to the axis of bending, if I look at, for example, in this case, okay, you get this kind of a strain distribution. So how do we get? let's say my if my neutral axis is I'm putting like this. Okay, so this is your neutral axis. Again, what is the bending axis? Let me. So this is your bending axis. So this is your bending. So your bending axis is this. Okay, so this is your bending axis, right? So you find that again neutral axis is not parallel to the bending axis. So once your strain neutral axis is fixed, then what we do, and I am talking compression in this side. So this epsilon cu is fixed, neutral axis is fixed, and then you can draw this strain profile. Okay. So once this is fixed and this xu is fixed, then I can draw this strain profile. So now you will find that in uniaxial bending, 1 and 2, let's say the layers of steel. Once you fix your layers of steel as y, the depth of the layer from neutral axis is y, uh, the bars in that particular layer were having same strain. In this case, if you look at it, though this layers 1, 2 are at the same location from cross-section point of view, however, when you look at it, one is going to be at a strain epsilon s1, which is this, and then 2 is going to be at this strain, okay, so which is this, which is your epsilon s2, but then 3 is going to be at this strain because you have this, and then epsilon s4 is going to be at this strain. So this is how you're going to get. So you will find that though these bars 1 and 2 and 3 and 4 are at the same locations from cross section point of view, now I'm considering the neutral axis at an angle. So you will find that all the four bars will have different strains, okay, which was not the case in case of an uniaxial bending. Okay, so then in addition to that, whether your neutral axis is within the cross section or not, now your stress block, compression stress block will be like this. Okay, so that we know that parabolic and then straight. Now, what is the area of your compression block? So let me. So that is what it is highlighted here. Okay, you find that your area of your compression block is not even for the rectangular section. It is not rectangle. It is a basically like a some kind of a polygon. So I have to integrate this area, which is this. Okay, this entire area is in compression. So finding the stress resultant is also more challenging, right? And so because I have to integrate the entire area, and the stress on each layer is also changing. Okay, so for example, this is your stress at this location, this is your stress at this location. Correspondingly, the width of that the polygon, you have 1, 2, 3. In this case, you have a 5 sides. So the width perpendicular to the stress is also keep changing, right? So integrating this to find that stress resultant or compressive stress resultant is also challenging. Okay, so these things, and you can find that again depending upon the neutral axis. In this case, if you see what that we have, we find that your epsilon s1, this is in tension. Okay, because this is the compression side and this is your tension side. Okay, right. So similarly, epsilon s2, epsilon s3, and epsilon s4. So you see here, once you fix this entire thing, this is below this is in compression. Whatever that is above this is in tension, right? So you see that only one bar is in tension, rest of the three bars are in compression. So, uh, but once you fix your neutral axis angle and the depth and your epsilon cu, then you can find out what are the strain on all the layers of the steel. Then from your respective quantity equation, we can also find the stress. Then when I multiply by the area, then you get all these forces also, CS2, CS3. This is also we can find out, right? Okay, so that is not an issue, but only thing is your compressive area, it is difficult to estimate this. Okay, in this case for the neutral axis angle and the depth that we have found, we find that you are having this kind of a five sided area. You can have a triangular area depending upon where you look at your neutral axis depth. For example, let's say my neutral axis depth instead of here, if I'm having neutral axis depth, let's say at this side, okay, at this location, okay, then this will be in compression. So you will have compression area. This will be the triangular area. Okay, so depending upon the location of the neutral axis of an angle, your compression area is going to change. So estimating the compression area and integrating them with stresses to find your net concrete compression force is going to be challenging. So this is one of the difficult aspects for doing the calculations, right? So in summary, what is that we are saying? To get your failure interaction surface for biaxial bending, you need to fix x and fix one value of angle of your neutral axis, then you get one point on the surface. So you repeat this exercise for multiple x and multiple angles of neutral axis, then you get family of points on the failure surface, then enclose those points to get the final failure surface. That is the way we can get your failure surface. Again, for uniaxial bending is a special case of biaxial bending where you get only one curve, okay, which is a 2D, two-dimensional curve. Here we are talking about a surface, okay. So that we have to keep in mind. And again, circular section is a special case because it's axisymmetric. Though you may have eccentricity about your x and y axes, that can be converted into an uniaxial bending, and your neutral axis will be always parallel to the resultant axis of bending, which will not be the case in case of a square column or a rectangular column. And your compression area also will change. You can have multiple shapes of compression areas depending upon the angle of neutral axis and the depth of your neutral axis, right?